In the next section, we're going to learn how we can solve oblique triangles. So remember, solving a triangle means to find any missing measures of either angles or sides. Now, what's special now is we have oblique triangles where we don't know if there's a right angle in the triangle. And generally, there isn't a right angle in the triangle. And if we have that oblique triangle, the methods we learned back in the first topics, the first unit, those methods don't work because they involve right triangles. So we have to develop other methods. Now, these methods have been developed already, but I'm going to show you where they come from. Now, generally speaking, though, how we proceed, whether we use the law of sines or cosines first, it depends on what information is given. So if we are given two angles and any side of the triangle. So if you took a geometry class and you learned about how to prove congruent triangles, you called those the angle-side angle or angle-angle-side situations. If you have either of those situations, if you're given an angle-side angle, two angles and the included side, or angle-angle-side, two angles and an opposite side, you are going to start with the law of sines. The other situation is if we have two sides and an opposite angle. So if you have two sides of the triangle and an angle that's opposite either of those given sides, that's the side-side angle. Now, if you remember, again, if you took geometry and you learned about congruency of triangles, we could not use side-side angle to prove congruency. And the reason is it's an ambiguous case. There could possibly be more than one triangle that has certain characteristics. So we have got to be careful in this situation. So if we have the side-side angle situation, we have to be careful. And we'll see why later. Now, if we have other information, if we have two sides and the included angle, if we have the side angle side situation, we will use the law of cosines. And if we're given all three sides, we will use the law of cosines. We'll see that in the next video. All right, so let's build the law of sines and see how we can use it. So, for the course, here's the basic diagram we're going to be using for our oblique triangles. The sides will be our English letters A, B, and C, and the angles will be denoted by the Greek letters alpha, beta, and gamma. All right, so I don't know that we've used that symbol before. Alpha, beta, and gamma. So A and alpha are opposite, B and beta are opposite, C and gamma are opposite. So let's build the law of sines. And it's actually fairly simple to build. One way to look at this would be, well, what I'm going to do is I'm going to take this diagram and I'm going to purposefully build a right angle in it. I'm going to go from the side labeled C and build a right angle, a perpendicular that goes to the angle with apex at gamma. So let me build this right angle here. And I'm going to label this height here, the altitude. Let me label it h temporarily. Well, then it's pretty easy, I think, to see then that the sine of the angle alpha is equal to h over b, and the sine of the angle beta is equal to h over a, using right triangle trigonometry. All right, so then take the first equation and multiply through by b. Then b sine alpha is equal to h. Let's take the second equation, multiply through a. Then a sine beta is equal to h. And if h is b sine alpha and h is a sine beta, then I can set those equal to each other. So then b sine alpha is equal to A sine beta. And let's divide both sides of this equation by the quantity A times B. So then we get what's commonly called the law of sines. The sine of alpha divided by A is proportional to the sine of beta divided by B. Now, if I had drawn a different altitude, I could get a similar statement using C and gamma. So then the sine of gamma over C is also proportional. And this statement is commonly known as the law of sines. All right, so in a triangle, in an oblique triangle, the sine of the angle divided by its opposite side is proportional to the side of any other angle and its opposite side. This is known as the law of sines. Let's see how we can use it. So let's solve this triangle. And here, again, I've drawn the triangle again for you. And now we're told that A is 92 centimeters. Beta is 47 degrees. Gamma is 32 degrees. So I have an angle, I have a side, and an angle, right? I have the angle, side, angle situation. Now, I can easily find alpha. The sum of the angles in the triangle is still 180 degrees. So I can easily find alpha. So let's first find the remaining angle. So then alpha is 180 degrees, subtract 32 degrees, subtract 47 degrees. All right, and I'll go ahead and calculate this on a calculator. All right, so let's see, 180 subtract 32, subtract 47. That's 101 degrees. Alpha is 101 degrees. All right, so I'll go ahead and label that in red. So alpha is 101 degrees. So notice this diagram is not drawn to scale, right? 101 degrees is obtuse. Obviously, what I've drawn here is not an obtuse angle. That's okay. We're not going to worry about that. Okay, now second, I'm going to use the law of sines. So let's see. Notice I have an angle and an opposite side, and I have other angles, right? I have, let's just say beta. I have beta, so I can use the law of sines to solve for B. So let's set up the law of sines. The sine of 101 degrees is to 92 centimeters, as the sine of 47 degrees is to the unknown measure B, the opposite leg, side. So now we can use a little bit of algebra to isolate B. So let's use cross products. B sine 101 degrees is 92 sine 47 degrees. And then use a little bit of algebra again. So B is 92 sine 47 degrees divided by the sine of 101 degrees. And then we can calculate this. So I'm not going to do any calculations yet, not until I write that, sort of exact form. Now I'll go ahead and bring up my calculator and actually calculate this. So let's make sure I'm in the right mode. I'm in radian mode. I need to be in degree mode. Let's switch to degrees. Go back to my home screen. 92 sine 47. Close off the 47. Divide that by sine 101. Close that off and hit enter. And that's 68.54. I'll just say, how about 68.5? Centimeters. So I now know that B is 68.5 centimeters. And then I can use a similar process to solve for C. I can't use the Pythagorean theorem, even though I've got two sides, because this is not a right triangle. So let's use the law of sines again. And so now I'll say, so now A I can use alpha and A, and I'll use gamma and C. So let's use the law of sines again. The sine of 101 degrees is to, again, 92, as the sine of gamma, 32 degrees, is to C. And so then using similar ideas, C sine 101 degrees is 92 sine 32 degrees. So C is 92 sine 32 degrees over sine 101 degrees. Sine 32 degrees divided by sine 101 degrees. And that's approximately 49.7. And this would be in centimeters. Now, if you're not getting those values, more than likely you're in the wrong mode on your calculator, so fix your mode. Now, a good thing to check really quick is, generally speaking, in a triangle, the smallest angle will be opposite the smallest side. And similarly, the largest angle is opposite the largest side. So that can be a quick check. It's not going to tell you if you did it right, but it's a quick check that tells you at least it's reasonable. So 32 degrees is smallest. C was 49.7. And looking at the sides, that's the smallest side. The largest angle is 101 degrees, opposite the longest side, 92 centimeters. So at least this is reasonable. All right, so I can be fairly confident that alpha is 101 degrees, B is 68.5 centimeters, and C is 49.7 centimeters. Let's see another example. So solve the triangle if alpha is 39.4 degrees, gamma is 72.2 degrees, and C is 19.2 meters. This would be a good time to pause. Try this one out on your own before I do it. All right, so let's see. Alpha is 39.4 degrees. Gamma is 72.2 degrees. And C is 19.2 meters. All right, and so what I have here is angle, angle, side. I have the angle, angle, side situation. And so again, this is a situation where we start by using the law of sines. Well, really we start usually by finding the third angle. So let's find beta. So it would be 180 degrees, subtract the 39.4 degrees, subtract the 72.2 degrees. So that's 68.4 degrees. Okay, so that's beta. All right, let me put that in here, 68.4 degrees. All right, now, see, now again, notice what I have. I have an angle and an opposite side. And so now I can use that in the law of sines to solve for either of the remaining sides. So, and it doesn't matter which one we solve for first. I'll find A. So let's see. I'll set this up as the sine of 72.2 degrees is to 19.2 meters. Sine gamma is to C as the sine of 39.4 degrees is to A. Cross products, A sine 72.2 degrees is 19.2 sine 39.4 degrees. A is 19.2 sine 39.4 degrees divided by the sine of 72.2 degrees. All right, and we bring up our calculator. .8. A is approximately 12.8, what are the units here? Meters. And then similarly, let's find B. So then sine of 72.2 degrees is to 19.2 as the sine of 68.4 degrees is to B. So then we go through some algebra. B is 19.2 sine 68.4 degrees over sine 72.2 degrees. And we calculate that value. .7 meters. All right, and so we've solved that triangle. So the angle-side angle and the angle-angle-side situations are basically the same. And they're the simplest situation, really, for the that we need to solve. The next situation, the side-side angle, that's the one that tends to cause some issues. So let's take a look at an example. All right, let's go right into it. If A is 673 feet, B is 1,240 feet, and beta is 52.3 degrees. So what I have here is a side, and then an angle not between them, but the angle outside of those sides. This is the side-side angle situation. And when we have this situation, we just have to be careful. I'm going to explain why we have to be careful in this situation. All right, so unlike the previous examples, I can't immediately solve for an angle just through addition or subtraction. I can't use the Pythagorean theorem to solve for the third side. I have to immediately start with the law of sines. So, here's what I'm going to say. I've got to solve for alpha. Let's find alpha. Because I have B and I have its opposite angle. I have A, but I don't know the opposite angle. Alright, so let's see. Then the sine of alpha is to 673, as the sine of 52.3 degrees is to 1,240. All right, so let's multiply through by 673. Then the sine of alpha is 673 sine 52.3 degrees over 1,240. All right, let's calculate that. So then sine alpha is 673 sine 52.3 degrees. Divide that by 1,240. So that's 0.42943, etc. So sine alpha is 0.42943. Don't approximate that too much. So then alpha is the sine inverse of that value. So let's calculate second the sine of the answer. Bring up the and the easy way to bring up the last answer on this calculator is you hit second and the negative button. It brings up your last answer. And I hit enter, and I get 25.4 degrees. But wait a minute. Let's remember how the function, the sine function, works. If we think of the unit circle for a moment, what we're saying here is, where is sine alpha 0.429, right? So if we think of our unit circle for a moment, sine is the b value. Where is the b value? 0.429. There are two possible angles. Here's alpha 1, and here's alpha 2. So alpha 1 is 25.4 degrees, or alpha 2 is 180 degrees minus 25.4 degrees, and that is 180 subtract the answer is 154.6. Now, here's the thing. In this situation, so now we have two possible values for alpha. We have to check, could both be possible? All right, so now, are both possible? Well, let's see. If we take alpha 1, then we need to find a gamma 1. Then gamma 1 would be 180 degrees minus the 52.3 degrees minus the 25.4 degrees. I can do that, right? I can do this subtraction. 180 minus 52.4 minus, 52.3 minus 25.4. It's 102.3. Gamma 1 is 102.3 degrees. What about if we take alpha 2? Alpha 2 was 154.6 degrees. Then gamma 2 would be 180 degrees minus 52.3, right? That was the beta value, minus 154.6 degrees. And I hope you can see that this is not possible. 180 degrees minus 208 degrees, that gets us into negative angles, which doesn't make sense in this context. So this can't be possible. So there's only one triangle, one actual alpha that's possible in this situation. Only alpha 1. So we're going to stop with the alpha 2. It's not possible. This alpha 2 is not possible. And we continue on with just alpha 1, gamma 1, and now we can find C. So now, sine of 102.3 degrees is to C, as I would go back and use beta and B. Sine of 52.3 degrees is to 1,240. Use cross products and a little algebra. C would equal 1,240 sine 102.3 degrees over sine of 52.3 degrees. And that gives us 1,531.2, 1531.2. And that would be in terms of feet. So in this case, there's only one triangle possible, and that's with alpha equal to 25.4, gamma equal to 102.3 degrees, and C equal to 1,531.2 feet. So here's a second example with the side-side angle situation. Now would be a great time to pause and try this one out on your own. Alright, so let's see what we have. If A is 42.7 centimeters, B is 30 centimeters, and beta is 38.9 degrees. Alright, so let's start off same as before. Let me solve for alpha. And again, though, notice that this is the side-side angle situation. And so we have to be careful in finding that first alpha. We have to remember how the sine function works. Alright, so then sine alpha is to 42.7 as sine 38.9 degrees is to 30.0. So sine alpha is 42.7 sine 38.9 over 30.0. And so then alpha would be the sine inverse of that quantity. Let's calculate that. So the sine inverse of 42.7 sine 38.9, close that off, divide by 30, close off the entire sine inverse and hit enter. 63.4 degrees. So alpha is 63.4 degrees, or alpha is 180 minus 63.4 degrees. So alpha 1 is 63.4 degrees. Alpha 2 is 116.6 degrees. Now, let's be careful. Do both work? If we take alpha 1, which is 63.4 degrees, then gamma would be 180 degrees minus 38.9 degrees minus 63.4 degrees. Gamma is 77.7 degrees. If, instead, alpha 2 is 116.6 degrees. Gamma would equal 180 degrees minus 38.9 degrees minus 116.6 degrees. And this time I think I can do this. 180 minus 38.9 minus, what is it, 116.6? 24.5 degrees. Both are possible. So if we take the alpha 1, we get a gamma 1 of 77.7 degrees, and if we take the alpha 2, we get a gamma 2 of 24.5 degrees. Both are possible in this situation, and so we have to solve both of the possible triangles. So we need to find a C1, and we need to find a C2, because there are two possible triangles on this situation. All right, so let's find C1. So using gamma 1, sine 77.7 degrees is to C1 as sine 38.9 degrees is to 30.0. Let's find C2. Sine 24.5 degrees is to C2 as the sine of 38.9 degrees is to 30. A little bit of algebra. C1 is 30 sine 77.7 degrees over sine 38.9 degrees. C2 is 30 sine 24.5 degrees over sine 38.9 degrees. And we can calculate each of these. So C1 is 46.7 centimeters. All right, and then we'd have 30 sine, was it 24 point, I forget. 30 sine 24.5 degrees divided by the sine of 38.9 degrees. C2 is 19.8 centimeters. So there's actually two solutions to this problem, and we have to state both of them. One solution gives alpha as 63.4 degrees, gamma as 77.7 degrees, and C as 46.7 centimeters. Another solution, a second solution, gives alpha as 116.6 degrees, gamma as 24.5 degrees, and C as 19.8 centimeters. And both are valid. All right, so we have to be careful with that side-side angle situation. We have to be careful and remember to check that we could get two possible angles and then see if both angles are reasonable with the rest of the exercise. All right, so that finishes up what we need for the law of sines.